Okay, so welcome back to live session 2. This session will be on this electron beam welding, laser beam welding, as you already know from your second week video courses, right? So, like the way we did in our earlier week, we'll go through some theoretical concepts. We will again brush up the uh, different kinds of laser welding and uh, the mechanism of laser sources, the mechanism of electron beam welding, and then we'll also do some numericals, right? Let us start then. So in question one, this is something on you need to identify the statement is true or false. So the first statement says that the main laser beam property that is exploited in laser material processing is the monochromaticity of laser beam. So is it true or false? Now, if you see laser beam property as such, coherency is the main laser beam property that is exploited in material processing, right? So I have kept this slide intentionally blank. So coherency is the main laser beam property that is exploited, right? So if you see if the two waves are monochromatic, like the way we have mentioned here, if the laser beam property are monochromatic, then what is monochromaticity? So basically their frequencies are the same, right? The two waves which you are considering, their frequency or wavelength, whatever you talk, those will be same. But can it be like the phase difference will be there? It can happen. Even if they are, even if your these laser beams are monochromatic in nature, their phases can be different, right? So even if the laser beam are monochromatic in nature, their phases can be different. So if the phases are different, can we talk about, can we tell this as a laser beam? So you have to have the beam to be incoherent, right? It should have move into some similar direction, right? So in laser, what will happen? All photons are of same frequency and same phase difference. So they will move in the same direction, right? That is why laser is coherent and kind of highly directional. So laser beam is coherent and highly directional. So what about the first statement? Is it true or false then? Anyone? Can you guys hear me? I cannot understand if you can hear me or not. Just anyone confirm you can hear me. Okay. So according to the discussion, these statements should be false, as I mentioned that coherency is the main laser beam property that is exploited in laser material processing, right? So this statement is false. And then in the second statement, it says stimulated emission occurs only when there is population inversion. So this is also a false statement. Now, if you try to understand physics of generation of some kind of laser light, so clearly there will be some kind of amplification of light, and the laser output are achieved by interaction of the atoms and molecules of some kind of active medium with the electromagnetic field of the pumping source, right? So in the laser beam welding, you have different what should I say, uh, different kind of units. So in between those units, pumping source is an unit, right? Now in an atom, if you see, there will be different kinds of orbits, as you know, 1s, 2s, 2p, 3s, 3p, 3d. So these are different kinds of orbits, right? And each orbit occupies certain kinds of energy levels. Now, a transition between states of this energy, let's say uh, I have some energy of E1 and E2, those results in some kind of emission or absorption of a photon. And if the frequency of this emission and absorption are, let's say this is nu, so what will happen of this E2 minus E1? So E2 minus E1 will be h nu, right? What is h? H is Planck's constant, right? Now, if you see in laser system, in to understand the physics of laser, there are three different obvious things, which are: first one is spontaneous emission. We call it spontaneous emission. Then second one we call it absorption, and then finally comes stimulated emission. So I hope these terms you are well aware of. Stimulated emission, right? Now, what will happen in spontaneous emission? So in spontaneous emission, let's say your atom is in some level 2, and here an atom in level 2 decays spontaneously to level 1. And when it is decaying from level 2 to level 1, uh, it adds some kind of excess energy in the form of a photon, right? So by definition, we say that for spontaneous emission, um, like the photon comes out in a random direction. So it is like if you have atoms like this, so 1s, 2s, 2p, 3s, 3p, 3d, so it can be emitted in random direction. But for a laser, you have to have some kind of similar kind of direction to have some coherence, right? So initially these are all spontaneous emission. Then you have this absorption where an atom in state one. So initially, so let's say this is my state one, and this is my state two. Okay, this is my ground state, and this is somewhere at higher state. And if you're applying some kind of energy over here, it will absorb the energy and will go to some higher state, and it will stay for some time, and then again it will come back to state 1. So what is happening in absorption? Basically an atom in state 1 absorbs a photon from the field, and thus it converts the atom into state 2, right? And there is some equation at which this process can take place. So the equation in terms of like, if there is n2 number of atoms, then So this is basically the number of absorbing atoms in the field, and the field from which they are extracting the energy. So there are some equation that I'm skipping, uh, and then after absorption there is finally coming this stimulated emission, right? So in stimulated emission, this process is kind of reverse of the absorption, and here the atom gives us this excess energy H nu to the field. Basically, it is adding some coherency to the intensity, and this added photon can have some kind of same frequency, same phase, same sense of polarization, and yeah. So stimulated emission, basically, you can say this is a process which is most significant for a laser, since it's basically provides you the energy or photons with the same frequency, same phase, same sense of polarization, as I was saying. And basically, this makes some kind of amplification of light, right, and possible, and produces some coherent laser light. So coming to the question, it says that simulated emission occurs only when there is population inversion. So population inversion is basically, uh, if you are having higher number of atoms at higher state compared to the lower state, then it is called population inversion. Okay. Now, stimulated emission can occur in normal state also. So, but in the normal state, what is happening that as the normal state, it has very few excited atoms, and probability of occurring stimulated emission is very low. That's why stimulated emission mostly occurs when there will be this population inversion happening over the region. Okay. And okay. Any question till now? Anyone? Any question? Okay. So we'll move to the third question. It says that there is no role of spontaneous emission in a laser. This is also false, because if you see, okay, let me explain in this way. So if you see a laser system, it must have some three basic components. What are those three basic components? What are those three components? So there will be some kind of active medium. What does it do? This active medium. So this basically serves as a means to amplify the light. So it amplifies the light. Then there can be some kind of pumping source, right? So what is the basic not mechanism? What is the basic operation of a pumping source? So this basically used to excite the active medium to the amplifying state. So excites the active medium to amplifying state. And you also will have some kind of optical resonator. So what does optical resonator do? It basically provides you some optical feedback. Now, the active medium may be any material that is solid, liquid, gas, or plasma. It is believed that something in everything will laze if the substance is heat hard enough, right? And the common laser mediums includes, it can have ruby, or it can have some ND-YAG laser, it can have some ND glass. So those things are there. And then any kind of energy source also can be used as a pumping source. So what are the common pumping source? So this common pumping sources include flash lamps. So these are kind of incoherent light. Then you can have lasers, which are coherent light. Then you can have electrons. In terms of electrons, there can be DC, RF, or pulsed gas discharge, or electron beam. There can be chemical reactions. There can be ion beams. There can be some kind of X-ray sources, whatever, right? And then, like in optical resonator, it causes the light generated by the active medium parallel to its axis, right, to be reflected back and forth through the medium. This is what optical resonator do. So if we try to draw some schematic, so it is like initially you have this active medium over here. So let's say this is my active medium, and then you have these are incoherent excitation input. Okay, and then what will happen? This is my active medium. Here you will have some kind of this population inversion taking place, population inversion, and then spontaneous emission, then absorption. And whenever this is in a state of population inversion, the output is coming as a stimulated emission, right? So it says that um, there is no, as I was saying, there is no role of spontaneous emission in a laser. Of course, this is not true. So when the pumping starts, some atoms of the laser medium will go to the excited state, right? I mentioned it earlier, and these atoms will undergo spontaneous emission initially and will emit photons. And these emitted photons will force the other excited atoms to emit photons, and then your stimulated emission will take place and laser action will start, right? This is how it happens. And okay, and then our fourth statement says laser action occurs only when there is population inversion. Is it true or false? What is population inversion? I told. So population inversion means there are more number of excited atoms in the system, right? So when you are having more number of excited atoms in the system, the probability of stimulated emission will be higher, as simple as that. And stimulated emission will ensure that emitted photons will be of same wavelength, same phase difference, and they will emit in the same direction with that of the absorbing photon, right? And this will in turn form that coherent laser. So yes, this action occurs only when there is population inversion. This is true. Yes, Gopi.
Yes, sir. Sir,
Mhm.
could you please explain the first question? The main laser beam property that is exploited in the laser material.
Yeah. So here the statement I mentioned that the main laser beam property that is exploited in laser material processing is monochromaticity of laser beam. What is monochromaticity? So monochromaticity is basically if you are having two waves, their frequency or wavelength will be same, right? So even if your frequency and wavelength are same, it can happen that the phases are different, right? So phase difference can be there. And if there is phase difference, can those waves can be coherent? Those cannot be coherent, right? Because to have some coherency, you have to have this similar phase of those two waves, right?
Yes, sir. Right.
Otherwise, it cannot move in the same direction. So that's what I have mentioned here that in laser, basically all photons are of same frequency and same phase difference, and that's why they move in the same direction. So here, not the monochromaticity, but the coherency is the main laser beam property that is exploited in laser material processing. So let's say I'm mentioning here coherency is the main laser beam property, right? Understood? Any question? Okay, great. So we'll move to the next question. It says absorbivity and absorption coefficient of a material for laser radiation are same. This is also not true, really. So if you see absorbivity, what is absorbivity? So it is kind of a fraction of some incident electromagnetic power that is absorbed at the interface, right? So if I let me write it here. So this is fraction of incident electromagnetic, can call it power, that is absorbed at the interface. And then I was saying about absorption coefficient. What is absorption coefficient? This is basically a ratio of the what should I say? Ratio of the absorbed electromagnetic power. and the incident power. Okay. Okay. Then my sixth statement says electron beam machining is a thermal process. What about electron beam machining? Of course, this is kind of a thermal process because here the heat for fusion is kind of obtained from the kinetic energy of a dense beam of high velocity electrons, right? So here the electrons are emitted by a cathode and thereafter it is accelerated by some kind of some ring-shaped anode, and this is focused by means of an electromagnetic field to finally impinge upon a very narrow area of the workpiece, right? So here the entire operation is carried out in vacuum with a pressure of something around some 10 to the power minus 3 mm of He. And here the accelerating voltage is in can be in the range of some 20 to 200 kilovolt. So these are some information regarding this electron beam welding. Uh, let's say try to draw some schematic. So I believe in schematic always. So how about drawing some schematic of electron beam welding. So we will have some kind of filament first. Let's say this is my filament, right? And then I can have this electrode over here. Then you can have this anode over here. Then you can have this some kind of diaphragm. We call it some positioning diaphragm. 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 And finally, you can have some kind of lens to converge the idiom, right? So you can have some focusing lens, right? So initially you are having this kind of thing, and then it is basically impinging over the workpiece at very high velocity, right? So here, when the applied voltage crosses the critical value, uh, this is like electron beam penetrating into the metal, and under such condition, if the workpiece is traversed relative to the beam, so an extremely narrow bit of weld can be formed, right? So the process is not suitable for a metal which vaporizes excessively or emits lot of gases when melted. Right? The process can be used to join dissimilar metals or reactive metals, or it can also be used for joints requiring some precise control of the weld profile or penetration, whatever you call it. So yes, electron beam machining or welding, whatever you call it, this is kind of a thermal process. Now it says electron beam energy is absorbed to the top surface of the workpiece. How about this? Any guess? Mhm. So, so what are electrons, right? Electrons are kind of smallest stable particle with a specific mass. You know the mass, electron mass. I'm not mentioning it, and it will have some negative charge, right? So when an electron is accelerated, through some potential difference, let's say I have potential difference of V. So then you will have some change in kinetic energy, right? What is the kinetic energy? So the kinetic energy is this half mv square. This is electron volt. Enough. So here me is the electron mass. U is the final velocity. U naught is the initial velocity, right? So when a fast moving electron impinging on a material surface, so it penetrates through a layer undisturbed. So again, let's say, so this schematic is to understand the movement of the electron below the surface, what is happening. So let's say this is my surface. This is my surface, and initially it will have some kind of transparent layer. This we call it transparent layer. And let's say this is my electron beam, which is impinging over the surface, and it will go through the transparent layer, and then it will basically decaying the velocity. Then this is my total range delta, right? So it basically it is starting colliding with molecules and ultimately it is brought to rest, right? So here the layer through which the electron penetrates undisturbed, that is called the transparent layer. This one, this layer is undisturbed and it is called transparent layer. And only when the electron begins colliding with some kind of lattice atoms and it starts giving up its kinetic energy, at that time the heat is getting generated, right? So it is clear that generation of heat takes place inside the material that is below the transparent skin. And there are some relation of this total depth of penetration. I am mentioning here because we are having some kind of numerical through this. So I'm not going into the derivation of this. So this is 2.6 into 7 v square by rho. Okay. So V is called accelerating voltage. V is accelerating voltage. What is rho? This is in volt, and rho is material density. Rho is material density in kg per mm cube. Okay, so electron beam energy is absorbed at the top surface of the workpiece. This is false because it penetrates, and then it is normally done in vacuum. Of course, this is true. And then it says that penetration depth of E-beam in a material gets doubled with the doubling of the accelerating voltage. What about this statement? So here, if you are doubling the accelerating voltage, so delta is proportional to V square, accelerating voltage. Will it be double or quadruple? Mhm. If delta is proportional to V square and you are doubling the accelerating voltage, what is happening with the penetration depth? Anyone, please? Can anyone respond?
Yes, sir.
Hmm. I cannot hear you, Gopi.
Sir, can you hear me, sir?
It says that uh, the penetration depth of a E-beam in a material gets doubled with the doubling of the accelerating voltage. This is true or false? If delta
Is
is
it?
proportional to
It can be true, sir.
how?
When we doubling the accelerating voltage, it can increase the
Yes, it
mm,
is increased, but
de-
numerically.
density increases the density of the atom denser.
So
That's
I'm
why
not.
the penetration depth is increasing.
Yes, I'm not mentioning anything regarding density here. Just assume that delta is proportional to the square of accelerating voltage. So if you are doubling the accelerating voltage, it is basically the penetration depth is getting 4 times. I'm not talking anything about here of at least. I'm not talking anything about this density of the material. Of course, if you are changing the material density, the penetration depth will react in different way.
Sir, I didn't said about material density, sir. I'm mentioning electron beam
I cannot understand.
density.
I cannot understand actually. You can maybe write to me or maybe mention it in the chat box. Do you have any chat box?
Yes, sir.
Okay. By the time we'll move to the next question. So you have to match column A with column B for this NdVAC laser. So there are also different kinds of laser. So you have the solid state laser where people use some kind of crystalline or glass rod which is doped with ions that provide the required energy state. Um, so in terms of dopant, neodymium is a kind of common dopant in various solid state laser crystals. Uh, so neodymium, okay. People also use this yttrium aluminum garnet, the YAG1 yttrium aluminum garnet, right? And solid state lasers are uh, kind of laser amplifiers also, where the light is basically guided due to the total internal reflection in a single mode optical fiber, right? So if you think of this fiber laser, here the light is guided due to the total internal reflection in a single mode optical fiber. Then you have this gas laser. What are different kinds of gas laser? You can have this CO2 laser, then you can have this helium neon gas laser, right? And then you can have these fiber lasers also. So here laser emissions is created within the fiber using some kind of semiconductor diode. So that semiconductor diode will be acting as some light source and delivered through a flexible optical fiber cable. So that's how this fiber laser works. And this is entirely solid state design that doesn't require some mirrors or optics, those kind of things. And then you can have this disc laser. So in disc laser, this is the pumping source is kind of diode, and like in disc laser, in terms of advantages, it can cool very efficiently. One of the advantages of disc laser, it can cool very efficiently, and the power and pulse energy that can be scaled to much higher values. This is easy to scale the power in disc laser. And then, as I was saying, you can have this diode laser. So that laser is kind of rapidly becoming an indispensable device in modern life. Uh, so in laser printers, in laser pointers, in some domestic CD player, all everywhere you are having this diode laser. And yes, this coming to this ND-WAG laser. What is the pumping source? What is the optical resonator? What is the active medium? What is the active center? Anyone wants to give it a try? So in ND-WAG laser, my active medium is yttrium aluminum garnet, right? What is the active center? This is neodymium, right? What is the pumping method here?
Shannon flash pump, sir.
Hmm. Yes. And the pumping method is optical pumping. So basically, the source what we use is xenon flash lamp, right? And then in terms of optical resonator, this is kind of some kind of rods, ends of rods which are silver coated, and there can be some multiple mirrors. So in general, two mirrors, of course, two mirrors which will be one will be partially reflecting, another will be total reflection, right? So we have this optical resonator, ends of rods, silver coated, and two mirrors. One is partially reflecting, and another is total reflecting. I hope I have mentioned all the things in terms of IndiVac. So you have this pumping source as xenon flash lamp. Then you have this optical resonator, which this end of rod silver coated. Then you have this active medium, and then you have this active center. Well enough. Should I move to next question then? Hmm. Okay, let's do some numerical. This is very basic kind of numerical. So it says that for ND wag laser, the pulse energy you are having 0.4 millijoule. What about the pulse frequency? This is 20 kilohertz. You need to find out the average power, and I am saying that let us consider your maximum power is your average power, and if your maximum power is the same as the average power, you need to calculate the pulse duration. For how much time the pulse will be on. What is the relation between average power and the pulse energy? So, pulse energy into frequency, it is equal to average power. Give me a number. How much it is coming? Anyone, please.
Sir, 8.
8. So, average power is coming as 8 kilowatt, right? So,
Yes, sir.
then I'm saying that let us consider average power as the maximum power. So, my peak power is also 8 kilowatt. Of course, this is not the real case. So for the numerical sake, I have mentioned it like this way. So let's say your peak power is 8 kilowatt and your pulse energy is zero point 0.4 millijoule. Pulse energy is zero point 0.4 millijoule. What will be the pulse duration? So if you have the maximum power, that into pulse duration on time, that will be equal to pulse energy. Is it not? How much is this coming? That T on. Hmm? How much this is coming? Am I doing anything wrong?
8,000.
How much?
8,000, sir.
I cannot hear you.
Sir, 8,000.
Yes, the power was coming as 8,000. Maybe in my options I think somehow I have made some mistake. But yes, the relation between this pulse energy and maximum power you can find out in terms of this. If you are having this maximum power and you have this pulse on time and you multiply those power into time, of course, this will give you the pulse energy. As simple as that. You know? Should I move to the next question? Just understand the concept. Maybe after so you can invest your time in finding the number. Okay. So it says which of the following process parameters are pertaining to micro laser welding. So this is in terms of something on laser welding, correct? Now I have talked about electron beam welding well enough. So in electron beam welding, you have this concept of acceleration voltage. You have this concept of velocity of electron. So those are in electron beam welding. And then if you want to understand this laser beam welding, just give me some time. What is okay? So in laser welding, of course, if you're looking into the question, as we are saying, this acceleration, voltage, and velocity of electron, those are related to this electron beam welding. Now, to understand what is happening in laser welding, so there are two modes of welding with laser, right? One is conduction limited welding, one we call it conduction limited welding. So, when does this happen? So, this occurs when the power density at a given welding speed is insufficient to cause some boiling and therefore to generate a keyhole, right? Now, here the whirlpool has some strong stirring force driven by, in my earlier lecture, I talked about this Marangoni type of forces. So, those results from the variation in surface tension with temperature. You know? So, most surface treatments in which this melting occurs employ uh, an out of focus beam, which results in conduction limited weld beam, correct? And the alternative mode is keyhole welding, in which there is sufficient energy per unit length to cause some evaporation and hence uh, a hole in the form of melt pool is formed. And this hole is stabilized by the pressure from the vapor that is being generated, right? So, yeah. Now, if we draw some schematic of this keyhole and conduction limited welding. Let me write over here. Keyhole and conduction limit. So in conduction mode, if this is my laser beam, the penetration depth is somewhere less than the keyhole mode. So you are thinking of this keyhole. This is kind of penetrating into the surface and making the depth very deep. So in conduction mode, basically the power density is less than the keyhole mode. And in conduction mode, you are heating the workpiece above the melting temperature without vaporizing, right? And here the penetration is controlled by the conduction mode. Now, what is happening in keyhole? Here, molten metal starts to vaporize, and your power density can exceed somewhere like 10 to the 6 watt per centimeter square. And when you are doing this keyhole, it opens up a blind hole in the molten metal, and your vapor pressure from that hot metal that keeps the hole open during the weld, right? And it kind of increase the energy efficiency of this welding process due to, so whenever you are having this penetration depth, you can have these multiple reflections of beam within the cavity. So you can have this multiple reflection like this, right? So in terms of differences, so let's say this is conduction mode, and this is keyhole mode, right? So one is your power density, this is less, this is more. Then you have this vaporization. Here it doesn't vaporize, here it vaporizes. Then in terms of this penetration, this is controlled by the conduction only. Here you have this vapor pressure from the hot metal, which keeps that blind hole open during the welding. Okay. So which of the following process parameters are pertaining to this laser welding? You have this laser scanning speed. We can have this pulse duration or pulse frequency. Also in conduction mode, you have this low welding depth. In terms of characteristics, you have this low welding depth. Then you can have this aspect ratio as small. Then kind of, what should I say, in terms of aesthetic thing, it is kind of very smooth and highly aesthetic welding bit. So this is smooth and highly aesthetic. And then in keyhole, this is, you're having this welding depth is high enough, aspect ratio is high enough, right? Okay. These I have already talked. Which of the following characteristics are pertaining to the keyhole mode laser welding? You have this high aspect ratio. This is not true. 1 and 3. Okay. Then one question from this electron beam welding again. I have already talked about little bit of electron beam welding. Now, what the things I have mentioned? So in electron beam welding, you have high energy density, right? This is kind of course, a fusion welding process. Uh, you are having this high energy density, then you have this bombardment of intense beam of electrons on the target materials. Then you have this instantaneous conversion of the kinetic energy into some thermal energy, and this impingement of electrons, those causes this weldment interface to mains and produce some weld joint, right? Now, in my schematic over here, where here, so the electron beam gun has a tungsten filament which is heated. This one. These are freeing the electrons, and the electrons are accelerated from the source with high voltage potential between this cathode and anode, and then the stream of electrons pass through that hole in the anode. This one, this was my anode, and the beam is directed by these magnetic forces of focusing and deflecting coils. You can have these deflecting coils over here also, focusing lanes and deflecting coils, and this beam is basically directed out and strikes the workpiece. And because it is striking the workpiece, the kinetic energy of the electron is transferred to the heat upon the impact of the workpiece and cuts a perfect hole at the weld joint. Enough. So here the molten metal fills in behind the beam and creates some deep finished weld. That's how it works. Now, in terms of principle, uh, the heart of this welding process is that generation of this beam from the this electron gun or column, whatever you say. The electrons are generated by heating a negatively charged filament, which is the cathode, to its thermionic emission, right? So we are having this thermionic emission temperature range upon which electrons are emitted. And those are accelerated by this electric field by negatively charged biased electrode that those are located in between that cathode and anode. I hope these things are well known for you. And then your electron beam can be focused under vacuum and strikes the metal surface at very high velocity. The electron beam can be focused. The electron beam can be. This is some information I want to mention over here. The electron beam can be focused over a diameter, the range of, right? And the key feature is its ability to perform this deep penetration welding with keyhole mode, right? So here it says that distortion presence in the electron beam welding sample is less as compared to the other welding process. Yes, this is true. Why? Because the electrons with high velocity impinged on the surface of the material is transferred to the heat and induces a maximum amount of weld penetration with the less amount of heat. This is also true, and this is correct explanation. So B is my correct statement. Okay. Okay, we are moving to the numerical now. So my final three questions all are numerical. Okay. We will do step by step and tell me if you are having any problem in understanding the numerical part. So here it says that the specific power of electron beam machining uh, for tungsten, this is 12 watt per millimeter cube per minute. Okay, so I have this specific power as 12 watt per millimeter cube per minute. And then it says we want to cut a 0.5 mm thick tungsten sheet with an e-beam at 12 meter per minute speed. So my thickness is 0.5 mm. My velocity is 12 meter per, sorry, 12 meter per minute. And then it says, though the focused e-beam diameter on the workpiece is 0.1 mm, so dB is 0.1 mm. The actual spot size is mainly governed by the heat conduction in the workpiece. It's fine. So what is the e-beam power required to cut the sheet and what would be the curve width? Basically the width of the welding region, the curve. You may assume the thermal diffusivity of tungsten, which is given alpha. I hope you are well aware of thermal diffusivity. So what is thermal diffusion length? What is thermal diffusion length? Are you familiar with this equation where alpha is your thermal diffusivity and what is tau? This is time, interaction time. No? Okay. Now, in general, if you see in electron beam welding, machining, whatever, so initially we calculate this thermal diffusion length or we call it D thermal, and then we compare it with the E beam diameter, the diameter of the electron beam, and then we say that if the thermal diffusion length or the I should not mention it as thermal diffusion length particularly for this numericals because this is kind of diameter. So if D thermal is greater than this E beam diameter, your curve width should be equal to the thermal diffusion one, and if it is not, then your curve width would be the E beam spot dia. Okay, so it's basically it is like if this is your electron beam and this is your diameter, right? So this is your spot dia. And if this is your workpiece, you are having a weld width of this dia, dB or D thermal, whatever. Now, if these things are mentioned, can we calculate? So initially, what we need to calculate, what is the e-beam power required to cut the sheet and what would be the curve width. So let us first calculate this interaction time, tau. What will be the time? What will be my time then? I need some more space actually. Okay. Just go with me and give me some numbers. Okay. So my tau will be, this is my interaction time, and I have my electron beam focus diameter, and I have my, what is V? V is the welding speed, right? Or machining speed. So if you have your speed and you have your beam diameter, this is your interaction time, correct? Is it not? So my E beam diameter is 0.1 mm, right? So if this is 0.1 mm, that means this is 10 to the power minus 4 meter, right? And my V is 12 meter per minute. So 12 meter per minute is how much? 12 by 60.2 meter per second, right? So this is my tau. How much this is coming? 10 to the power minus 4 by 0.2. This is coming as 5 into 10 to the power minus 4 second. Okay. Now I got my interaction time. Then what will be the diffusion length or the thermal diffusion length? This is 2 root alpha tau, right? Now I know my thermal diffusivity of tungsten, which is provided. That is 2 into root over 6 into 10 to the power minus 5 into, now tau is 5 into 10 to the power minus 4, right? Now this is in terms of meter square per second. This is in second. So what will be my D thermal? This is 6 into 10 to the power minus 5 into 5 into 10 to the power minus 4.
7.745 into
How
10
much?
to the
How
power
much?
minus 4. 7.745 into 10 to the power minus 4.
Well, just wait. For me, this is coming as 3.46 into 10 to the minus 4 meter. Are you getting same value? Okay, just go through it. Uh, this is what I am getting. Let me know if I am wrong in my next station. So here my thermal diffusion length is coming as something around 3.46 into 10 to the minus 4 meter, and my dB is how much? So it's only 10 to the minus 4 meter, right? So my thermal diffusion length is greater than the E-beam spot diameter. So what about the curve width then? My curve width will be same as the thermal diffusion length. Correct? Now, if I got my curve weight, that is W weight, and then you have your thickness, you also have your velocity, and you also have your specific power, all multiplied together will be equal to the power, is it not? So your specific power is in terms of watt per millimeter cube per minute, and you have your material removal, or if you are doing some machining, this is your material removal rate, width into thickness into velocity. Correct? So my power is equal to, this is 12 watt per millimeter cube per minute, which is 12 into 60, that divided by this. This is in terms of watt per meter cube per second. And then you need to multiply it with what? This is your 3.46 into 10 to the power minus 4 meter, this curve width. And then you have this, what is the thickness? 0.5. So this is 0.5 into 10 to the power minus 3. This is meter. And then what else? Your velocity. This is 12 meter per minute, which is 0.2 meter per second. Right? You just multiply it all together and then get the value. Any question? My second question is just similar to this question 7. So if you have any question, please ask me now. I expect that will do my next question. No question? Yet. So let us move to the next question then. So here it says, here it says, a micro hole is to be drilled in 500 micron thick tungsten sheet with an E-beam focused to 100 micron diameter. Okay, so let us put all the informations together first. So your thickness is 500 micron, right? Then you have this diameter of E-beam is 100 micron. Then you have this power of E-beam is 10 kilowatt. Then it asks that what should be the E-beam pulse on time to get it affected zone free hole drilled, the focused E-beam diameter at the workpiece surface, and what will be the total drilling time. So in terms of these thermophysical properties, I have rho, the density, as this 19,300 kg per meter cube. And then I have specific heat, which is 140 joule per kg Kelvin. Then I have specific power, which is again I have kept it as 12 watt per millimeter cube per minute, which was you need to convert it in terms of watt per meter cube per second. And you have this thermal conductivity also, which is 164 watt per meter per minute. Sorry, watt per meter Kelvin actually. Watt per meter Kelvin. Okay. Now it asks that for producing holes with negligible heat affected zone, as I have already mentioned, you need to first identify what is this thermal diffusion length, and then you need to find out is it smaller or greater than your E-beam spot diameter. What is thermal diffusion length is coming as 2 root alpha tau, right? And then, okay, so there is one assumption here which I have not mentioned in the question. So, if you want to produce some holes with negligible heat affected zone, the operation you should conduct, it should be in pulsed mode. So, there is continuous mode operation and there is pulsed mode operation. Okay. Now, here we are assuming that because the heat affected zone is very negligible, this E beam spot dia is equal to the diffusion length. So basically dV is equal to d thermal. Okay. Now can we proceed? So if your d thermal is equal to dB, so 100 into 10 to the power minus 6 is equal to 2 root alpha tau. What is alpha? What is thermal diffusivity? I'm sure you are well aware of these things. Alpha is K by root Cp. Is it not? This is thermal diffusivity, right? So my tau will be finally coming as 1 by alpha into. You please spare some time with these numericals. Maybe for this short time, this will be a little bit difficult to absorb. But yes, if you keep some time, it will be well understood, I think. So my tau is coming as this 1 by alpha into dv by 2 whole square. And alpha is k by rho cp. So this is rho cp by k and dv by 2 whole square. So this will be coming as tau is equal to 19,300. This is in kg per meter cube, which is rho. Cp value is 140 joule per kg Kelvin. This is Cp. K is 164 watt per meter Kelvin. This is conductivity, and that into my dV is 100 into 10 to the minus 6, that divided by 2. So 50 into 10 to the minus 6, that whole square. How much this is coming? Just right. 19,300 into 140 to 15 to 10 to the minus 6. That's whole square. That divided by 164 equal to. So this is for me coming as 4.12 into 10 to the minus 5 second. Okay. Uh, I'm doing the calculation. Please do this in your spare time. So this is my pulse on time, right? The interaction time. Now I have my specific power as 12 watt per millimeter cube per minute. What I need to find out the total drilling time. This is my pulse on time. Then what will happen for the total drilling time? I have my total power. I have my specific power. That into Q. Q is what? Q is equal to MRR, material removal rate. What is material removal rate here? Hmm? So I have my specific power. What is Q? If I having this area of machining, and you have this thickness of the workpiece, that divided by time. Is it not? So what is area? My area will be 5 by 4 dB square. So if you have this spot dia as dB, your area of machining is 5 by 4 d square. Correct? Then you have your thickness, which is provided already. Thickness is 500 into 10 to the minus 6 meter. This is meter. Correct? And what else? You have the specific power. I know my specific power, which is 12 watt per millimeter cube per minute. I need to convert it to watt per meter cube per second. So 12 into 60, this millimeter cube, so 10 to the minus 9. Okay. So this will be coming as 12 into 60, 7.2 to 10 to the power 11 watt per meter cube per second. I have my specific power. This is known. I know my area. I know my thickness. And do I know power? Yes, 10 kilowatt power. Power is also known. So you can find out the total drilling time. Is it? So power known. Power. I'm not calculating it. Power, area, thickness, and specific power. These are all known. You can find out the total drilling time then. So I have already calculated this numerical. Just confirm maybe in the next session that this is coming as 2.0 8 into 10 to the minus 4 second. Okay. Any question in the concept? Any concept you have not understood? And my last question. Before that, if you have any question, you can ask. Okay. So, if you do not have any question, let us try to solve my last numerical, right? So, here it says 1 kilowatt fiber laser beam is being used to cut 3 thick steel bed with O2 gas assist. So, uh, my power is 1 kilowatt. My thickness is 3 It is 3 into 10 to the minus 3 meter. Then it says the divergence angle of the laser beam. What is divergence angle of the laser beam? So if you are having, this is my laser source and this is my laser beam. This is my half divergence angle right now. So it says 2 theta is 1.5 milliradian, correct? So 1.5 into 10 to the minus 3 radian. Okay. And then it says my focal length f. F is my focal length, which is mentioned as 100 mm, which is 100 into 10 to the minus 3. Okay. And then I have my, what else I have? What would be the focal spot diameter laser power density? Assuming that curve width is equal to the spot diameter, 70% laser power is absorbed by the sheet and 50% absorbed laser power is added by the exothermic reaction. I think something is missing. Something is missing here. Can you guys guess what is missing here? Hmm. My wavelength of the fiber laser is missing. Here I have not talked about the wavelength, the lambda value. So in general, for fiber laser, it is usually something around 1 to 2 micron. So let us take it as 1 micron wavelength of the laser beam. Okay. So this is coming as 10 to the power minus 6 meter. Please consider it into this numerical value. Now, what I need to calculate here, I have my beam divergence angle. So, what do we know in terms of beam divergence angle? theta is lambda by pi w naught. Is it not? Let's go through the lecture series maybe. So your lambda is the wavelength of the laser, and then this is your beam radius. This is your beam radius, correct? Yeah. So if this is your beam radius, so this is 2 lambda by pi dB, right? dB is laser beam diameter. So my theta is provided over here. You need to find out dB. So dB is coming as 2 lambda by pi theta. So 2 into 1 micron, 2 into 10 to the minus 6, that divided by pi into this is theta. I have value of 2 theta. So 1.5 into 10 to the minus 3 by 2, that into 2, right? So this is coming as, I don't know how much. Let us see. 4 into 10 to the power minus 6 is equal to that divided by pi into 1.5 into 10 to the power minus 3. So this is coming as something around 8.5 into 10 to the power minus 4 in meter. So you have this BV value. Now, what will be the focal spot dia then? If this is my laser beam dia, what will be the focal spot dia? These were all in that lecture note. Okay. So if you have this beam dia, what will be the focal spot dia? I need to find out the focal spot dia, right? So theta is something around focal spot dia, that divided by 2f. What is f? It is the focal length, right? So I am considering a pure Gaussian mode. Here it is mentioned that consider TEM00 mode. So your m square value will be equal to 1. This is for pure Gaussian mode. I hope that you know that there are different modes of laser beam. So that's why there will be different m square value. I'm not going into that. So if you are having m square equal to 1 and theta is something around this focal spot dia by 2f, which is the focal length, you will get df is equal to 4 lambda f by pi dB. This is my final expression of focal spot diameter. Okay. So my dB is coming as 8.5 into 10 to the minus 4. 4 into how much is lambda? 10 to the minus 6 into how much is f? This is 100 into 10 to the minus 3. That divided by pi into dB, which is 8.5 into 10 to the minus 4. This is in meter. How much this is coming? 4 into 10 to the minus 6. This into 100 into 10 to the minus 3. That's equal to by pi into 8.5 into 10 to the minus 4. For me, this is coming as 1.5 into 10 to the minus 4 meter. So this is coming as focal spot dia. Okay, just correct me if I'm wrong in the next session. So if I am having this focal spot there, you need to finally find out what will be the power density. What will be the power density then if you know the focal spot there? So it's simply total power by pi by 4 into df square. Is it not? So you have this 4p by pi df square, correct? So you have this 4 kilowatt. You have this 4 kilowatt, 4 into 10 cube by pi into 1.5 into 10 to the minus 4. Hmm. So this will be my power density. Okay, I think I should stop here. If you have any question, in my earlier lecture video also, I have provided my mail ID. You can mail me anytime. We'll meet tomorrow again. Bye bye.